Okay, this is Module 18, Prove Theorems about perpendicular lines. First thing is more theorems to learn. Theorem 3.8, and again, do not know this by Theorem 3.8. You have to know it by the actual definitions. But basically what it states is that if two lines intersect to form a linear pair of congruent angles, remember linear pair forms a line. It's a pair of angles, and they are adjacent angles. That's from Chapter 1, or from module, the first few modules. The linear pair of congruent angles, then the lines are going to be perpendicular. The main reason is because, well, they have to be congruent, and they form a linear pair. What does a linear pair form? It's 180 degrees. So we know, because of this, it's 180 degrees. So that automatically means, and this is putting it in notation, if angle 1 is congruent to angle 2, we know that G is going to be perpendicular to H. G's line is going to be perpendicular to H's line. This theorem here, 3.9, is actually going to be used a lot. And what it states is that if two lines are perpendicular, then they're going to intersect to form four right angles. So, if we know that line B and A are perpendicular, that's the notation, we can say that angle 1, angle 2, angle 3, and angle 4 are going to be right angles, which means, by definition of right angles, they're all going to measure 90 degrees. Okay, so we have in the diagram, I tell you that AB is perpendicular to BC's line. What can you conclude about angle 1 and angle 2? Well, if I tell you that that AB is perpendicular to BC, by this previous theorem, 3.9, we can state that AB and BC create right angles. So we know they form four right angles because of the theorem of two lines intersecting to form, the two lines that are perpendicular, they intersect to form four right angles. If we know that they are right angles, we can also conclude that angle 1 is congruent to angle 2 because all right angles are congruent. That was proved in a previous module. So, we used, if two lines are perpendicular, they form four right angles, to show that angle 1 is congruent to angle 2. Okay, this one, if another theorem, if two sides of two adjacent, remember adjacent is they have to be right next to each other sharing a side, acute angles are perpendicular. So we know that the two angles are going to be acute, but we know that two sides of them are going to be perpendicular. We can state that they are complementary, and the reason we can is because perpendicular angles, or perpendicular lines, create 90 degrees. And if we have two angles that form 90 degrees, we call that complementary. So if we have the diagram to the right, we have angle ABC. It shows that AB is perpendicular to BC, or BA is perpendicular to BC. Doesn't matter. We can conclude angle 1 and angle 2 are complementary because if we have two perpendicular angles, or two perpendicular lines, and those form two adjacent angles, because you have a ray that's going through the middle here, we know that those two angles are going to be complementary. Okay, so I have a proof, and right now, again, the proof is we're going to fill it in as we go. So it states, prove that if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. So we're basically proving Theorem 3.1. So, what do we have to work with? We are given that ED is perpendicular to EF in the diagram. So, that's what we're given, that's what we start off with, and we say, that's given. But how do we know that DEF's angle is a right angle? Well, from a previous theorem, if two lines intersect to form are perpendicular, they're going to form four right angles. So perpendicular lines intersect to form four right angles. Now, if we have established that DEF is a right angle, how do we know, going from here to here, how do we know that DEF's measure is 90 degrees? Well, that's what the definition of a right angle states, that if you have something that's a right angle, it measures 90 degrees. Okay, so we know measure of angle 7 plus measure of angle 8 is equal to DEF. This is something from a long while modules ago. And basically it says if you take two angles, add them together to get a larger angle, two smaller angles, for example, angle 7 plus angle 8 gives you the entire angle DEF. If you do that, you're adding two angles to get a larger angle. That's the angle addition postulate. Now, from 3 to 4, or I'm sorry, from 4 to 5, we have measure of angle 7 stays the same. We have plus, and then measure of angle 8 stays the same. How do we make DEF's measure become 90 degrees? Well, we took what's in step 3, and we substituted it in to 90 degrees. So, from step 4. So that's the substitution property. DEF became 90 degrees. Now, if we have established that two angles add up to 90 degrees, how can we state that angle 7 and angle 8 are complementary? Well, this guy here, is the definition of complementary angles. So we know by definition of complementary angles that angle 7 and angle 8 are complementary. Okay, some more theorems. We have the perpendicular transversal theorem. And basically this states if a transversal, remember that's something that cuts across two lines that are coplanar, intersects at two different points. So we have an intersection here and an intersection here. If a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other. Well, how do we know that? Well, if you recall from a previous module, what are these types of angles called? Well, those are corresponding angles. And if we have established that the lines are parallel already, we can use previous theorems to actually show another theorem. So we state if H is parallel to K, and we also know that J is perpendicular to H, we can automatically conclude from this that the J line is also going to be perpendicular to K's line because it's already perpendicular to one of the lines that's parallel to the previous. So these two lines are parallel, and that's actually can be proven by the corresponding angles theorem. So, theorem 3.12, lines perpendicular to a transversal. Again, this is using previous theorems to prove, but in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Now, this is not, you can't immediately say, well, they're corresponding angles, so the corresponding angles are congruent. That means they have to be perpendicular, or that the lines are parallel. You have to use a theorem that actually shows that the two lines, M and N, are parallel because of the corresponding angles. Since we don't know that the lines are parallel, we know that the corresponding angles are congruent first. So corresponding angles are congruent. If we know they're congruent first, that means we can conclude by the corresponding angles converse, this is in a previous module, that M is going to be parallel to N's line. So what you can say is if M is perpendicular to P, and we know N is perpendicular to P, then we can conclude that M is parallel to N. And you prove that actually by the corresponding angles converse. Okay, so using the previous theorems, it says determine which lines, if any, must be parallel in this given diagram. Okay, so I'm looking at this. I immediately look and see, okay, I've got a corresponding angle here and a corresponding angle here. So I look and say, okay, those are corresponding angles. So I can actually show that by the corresponding angles converse that S and T are parallel. But we also have a theorem that states that if two lines are perpendicular to the same line, then they're going to be parallel to each other. So that's one. We have P and Q, which are going to be parallel because they are both perpendicular to line S. We also know that lines S and T, these two guys, are parallel as well because they are both perpendicular to line Q. So, using the previous theorems, we actually show that we have S and T that are parallel. We also have P and Q that are parallel, and that's it. Okay, for the next one, we have is B, for the next diagram. It says, is B parallel to A? And is B perpendicular to C? Okay, well, let's look at the B, is B parallel to A? So we have A here, we have B here. Well, I look at this, and I see that they are both perpendicular to line D. So if lines A and B are both perpendicular to the same line, that means they have to be parallel to each other. That's by the previous theorem that we just showed. Okay, let's do the next one. Is B perpendicular to C? And this one's actually a little harder to do. You have, first of all, I noticed in this diagram that these two guys, these two angles, we have C and D are both perpendicular to line A. That automatically means that C and D are parallel. If we know that C and D are parallel, that means D is perpendicular to this line, or B is perpendicular to D. We also know, since they're parallel lines, that C has to be perpendicular to B because of the perpendicular to a transversals theorem. Therefore, we know that B is perpendicular to C by the perpendicular transversals theorem as well. So we just did it, we used it twice. Okay, distances. This is going to be something you're going to be using in later modules, specifically when we get to triangles. We're going to be talking a lot about distances. But this particular one here is probably the more important of the two, or the more prominent, I should say. But the distance from a point to a line is going to be the length of the perpendicular segment from the point to the line. So if I draw a segment, it has to be perpendicular to represent a distance. Okay? So if I drew a line that's kind of random, like this, to K, and measured it with a ruler, since I don't have a right angle, I can't say that it's a distance. It has to be the line that's perpendicular, or the perpendicular segment from the point to the line that we're measuring. Okay, the other thing is the distance between two parallel lines is going to be the length of any perpendicular segment joining the two lines. So again, you have to find the distance, and it has to be a perpendicular segment. So it cannot be, for example, a random point here and then a random point here, and then you measure from here to here. That's measuring a distance, but it's not measuring the distance from line M to N. It has to be the perpendicular segment.